Good morning everyone. Today we're going to be taking a look at how I created this procedural smoke setup. So quite often when I'm working, I like to try and avoid simulation when I can. The reason being, in production environments you have access to a render farm, which means that when you're caching out geometry you can actually access maybe as many as 20 or more machines when you're working. However, a simulation has to run generally on a single machine and do one frame followed by another frame. So a 50 frame simulation at 30 seconds a frame would take you 25 minutes to cache out a single version. And at the end of it, you might not like what you have, so you have to change settings and then go through it again and have a whole nother 25-minute per iteration. Whereas procedurally, like this, you can do your setup. The setup might take you, in this instance, it takes around about half an hour to an hour, depending on how much I'm talking. But then when you send it to the farm, if, for example, you could gain access to 50 machines at one instance, even if it's still taking 30 seconds a frame to calculate the procedural smoke, in theory you could get the whole lot back in 30 seconds, take a look at it, see what changes you want to make, change them, send it back again. So you can get 10 versions in half an hour quite easily. So you can really push the look. And of course, if any of the geometry changes, so the input animation changes, you just need to switch over to the new geometry and it'll all pick up and that'll work fine. Okay, so let's dive into Houdini and have a look at how we're going to do it. Now I'm assuming that this object, if I look through the shot camera, has come from a previous department. I don't want to touch this, I want to leave this as it is, so I create a second object which I will call effects_smoke trail, and this is where I will create all my effects. I'll have a second object which I will call render smoke trail, and this is generally how I work. This is my working node. There will be an out node at the end of this inside. And that is why I object merge here. So it doesn't matter where I leave my display flag in here, it will always pick up the right node. Okay, so diving inside the effects node, let's generate an object merge and find the out node for the input geometry. Okay, so we've got the geometry coming in. I'm just going to hide other objects for now just to make things a bit cleaner. Okay, I'm going to add a trail node. So this trail node, by its default function, it will give you essentially timestamps of the input geometry. So if I were to set this, for example, to 24, which is generally a second of footage in film, it gives you 24 stamps, and that is how far this object has travelled in 1 second. However, I don't actually want to do the whole geometry. I want just a few points. So I'm going to throw down a scatter node. And before I plug it in, I'm going to tell it to only create 10 points. So then this 10 points will get duplicated 24 times, and I get these trailed points. Now what I want to do is I want to convert these points into polygon curves. A good way to do this is with the add node. Now by default, when you switch this to the correct function, which is polygons, it will add a polygon by group, so it will start at point 0 and it'll create a curve that starts there, and it'll go to point 1, point 2, point 3 and so on until it gets to the end, which in this case is point 239. Which means it's spiraling round and it's not really going to give us the results we want. I would like each point to have a curve from the start. So each of the 10 points from this scatter, I want a curve to pass through. So we need a way for that add node to know that there is a correlation between points on different iterations of the trail. So at this point I'll create an attribute wrangle. Drop it down there. I'm going to call this attribute wrangle ID. Good is a good practice to name your wrangles, particularly because the functionality can be so random. You know, a scatter node, it's doing a scatter, and a trail node, it's doing a trail, but an attribute wrangle, who knows what's going to be going on in there. So I just say I for integer at id, so this is going to create an integer value on the points, equals I at pt num. So pt num is an intrinsic property of the points, and you can call that without it having been pre-declared. If you want to know some of the other things that you can call that way, if you drop an attribute vop, an attribute vop down, dive inside, all of these can be declared in the same way. So p and v and force are all vectors. Age and life are both floats, and so on. And there we go, pt num. For primitives, it's prim num, and you've got vertex number. Num pt is the number of points. So yeah, this is a really useful thing to check out if you've not done so before. So what I've done, I've said that the ID is equal to the point number. Looking at the geometry spreadsheet, we can see 0 to 9 on the point number and 0 to 9 on the ID. However, if we look at the trail, we've got 0 to 239 on the point number, but the IDs cycle through 0 to 9. So each point has now got a correlation with the others, and we can implement that on the add by saying by attribute, and the attribute we're looking for is ID, and there we go, we've got these lovely trails that follow through. And again, do not forget that this is a procedural setup. If you want to change anything, you can do. Change the length of the curve, so you could change this to 70, taking it almost to a completely full circle. Or you could drop it down to 12, or any number you're after. You could increase the number of points that you are scattering to get a denser trail cloud there. I'm just going to keep things at the moment to 10 and 24, just to keep things at a reasonable baseline. Now, as you saw, this trail will animate and move with the input geometry. However, there's no movement to them. They don't have any dynamics or any life. Well, we're not going to add actual dynamics, we're going to add fake dynamics. I'm going to use an attribute vop, and I'm going to use noises to displace the curves to add animation to them. So inside, if I create an anti-alias noise, if I drop it down, plug it in. So this noise, it is one of my favourite noises. It is zero-centered, meaning that it'll give you values both above and below 0 in roughly the same proportion. It also has the advantage that you can have multiple types of input and multiple types of output. If I just cut this node initially, you can see all the different types. It can have 3D, 1D, 4D inputs, and 1D and 3D outputs. What we're after is a 4D input and a 3D noise. So what does that mean, a 4D input? So P is a vector. It's got 3 dimensions to it. It's got X, it's got Y, and it's got Z. We want to have this be a 4-dimensional input, so that we can use time to be the 4th dimension that will drive the evolution of the noise. So on this 3D input mode here, the anti-alias noise has 3 sections for position, frequency, and offset, and we want to use a vector-to-vector 4 node just here to change that to a 4D option. When you plug that in, it will give you a 1D output by default. We want to change that to 3D because we want to add 3-dimensional noise to this 3-dimensional point position. So if I just do an add node, it's literally add P and the noise. And when we plug the outplug of P into there, we can see we've broken up the shape of this slightly. Let's just promote a couple of parameters. So we've got some artistic controls. I'm going to promote the frequency, I'm going to promote the offset, and I'm going to promote amplitude and roughness as well. Missed. There we go. Cool. So now if we just push the amplitude up to a higher value, let's give it a value of 7. you can see that this looks, again, it's looking a little bit like garbage. Now the reason for this is that we generated 24 points for each curve, which isn't really enough resolution point-wise to reflect the detail of this noise. So by using a resample node, we can increase the resolution of that curve. So you can see here we've got much more detail going on. We could probably get a little bit more out of there. There we go. Now that is a much more detailed noise. Excellent. Right, let's turn that off. And it looks a little bit chaotic. If we were to show all objects so we can see that, yeah, this does not really look like something trailing from that rock. It just looks like a massive weird curves. A couple of reasons for that. The main one for me is that everything is static, for one, and everything is always at the same amplitude. So if it's really big here, it's really big here. So what we can use on this resample node is we can use the curve U attribute. This generates a 0 to 1 attribute that you can see in here. We have access to that, and that means that we can use that to multiply down the amplitude of this output noise before it gets added to the world position. So if we bring in that curve view and call it curve view, so that's a bind node to bring in the attribute, and then you type in the type of the name of the attribute that you want, and you can select the type here. We are using a float, so that's fine. I'll add a multiply node to the output of the noise before it goes to the add, and then I'll click the input in. There we go. So you can see here it has low to no amplitude, and as it goes down it gets higher and higher. If we scrub the timeline, you can see that that has a little bit more look, a bit more life. There is some growth and movement going on, which is cool. We might want a little bit more artistic control, so I'm going to create a ramp parameter. Ramp parameters take a 0 to 1 input and give you a remapped 0 to 1 output. Well, technically it doesn't have to be 0 to 1, but if you're using it in the standard way it will be. I'm going to call this ramp curve U ramp and give it the label of curve U ramp as well. I'm also going to change the ramp type to spline ramp. When you do this, even though the default looks like it's going from 0 to 1, if you go up a level you will see that it's all zeroed out. If you control middle mouse click on there, it will revert to the default value, and then you can start playing with the settings to get something that you're after. Cool. So just on this on the topic of ramps, here everything is interpreted linearly, so it's a straight line from point A to point B. I would like a slightly smoother interpolation, so I'm going to click the first node in the ramp, shift and click the last node, and then set it all to B-spline, so we get a much smoother interpolation. Cool, okay, so we've got that sorted. That looks interesting. I'd say the amplitude looks good, but I'd say the frequency is a bit high, there's too much noise going on. Things we could do, we could drop the roughness right down, which does work. I'd say that the shapes maybe are still a little bit twisty, so I might drop down the frequency just to get less detail in there, which works quite nicely. The one thing that I can note is everything with this low frequency is receiving very, very similar offsets. I'd like to break this shape a bit so it doesn't just look like a single turbulence has been applied to the whole thing. So what we can do is we can give everything an offset in that fourth vector field. So we have on this vector effect 4 node an input which will dictate the value of this fourth component. We can plug ID because every curve has a different ID, so this can be the seed for that. Although I do want to be able to control how much this offset is applied. So I'm going to create a multiply node, and I'm going to promote the input for that, and I'm going to call this ID underscore mult, ID mult, there we go. And then into that second input, I'll plug the ID. Cool. Okay, so if I go up now, I've got this control, and if you watch as I increase this, it starts to add variance to each curve. And you can keep going, you can go above one, you can go outside the range of a slider. If you do think that you're regularly going to go outside the range of one of your inputs, you can just change the range here just to make the interface more usable without having to scroll out. I think I'm going to stick to about there, and now you can see we've not got that weird pushing around of the whole shape. Everything's a bit more independent. The final thing we'll do is we're going to add some evolution to the noise so that it changes over time. I'm going to do that in the fourth field of the offset. I'm going to say $t times 0.1. So that's saying go 10% the speed of time, basically, is the evolution. Nice and slow. So if we go through now, you can see that the shapes start to change a bit, which is cool. Okay, now let's convert these curves into a volume, into smoke. To do this, we're going to use rasterize particles. There are a few rasterize nodes. There's this rasterize attributes, which is fine. All it is it's a wrapped up version of rasterize particles. You feed in a number of attributes and it runs over it however many times you've said. But we can use the raw node. Avoid using the rasterize points for this sort of operation because it's not as quick as rasterize particles. This requires two inputs. It requires a base volume and it requires a particles to rasterize. So to plug the particle field straight in there, I'm going to create a volume field just here. Plug that into there. So this volume will be the same size as the bounds of this input object. I'm going to call this density, and I'm going to say I want it to be, this is the voxel size that you're working with. If you middle mouse, you can see it's got the voxel size, which will be a close approximation to what you've set there, which is cool. Okay, so then plugging that into the rasterized particles, let's see what we get by default. So we've got this big cloud. So this particle scale is saying how much, what the radius of the volume it's going to stamp onto each point is. So by default, it's 1. That is a multiplier. So if you were to drop this, say to 0.2, you get something a bit more useful. But it is worth noting that you can feed an attribute into it from the points itself. So if I left this at 1 and created an attribute wrangle here and said f at p scale equals chf, so that's a channel float, and I say p scale here is the name of the attribute. When I click the plus, it's going to create a little handle to control this p scale value, like so. By default, it will be 1, but if I set this to 0.25, for example, there we go. I can control outside what we're doing. Now, why would you want to do it outside as opposed to internally? Well, this is just a global multiplier. It will apply to every particle, whereas here you could start doing things like ramping things by curve view again. We're not actually going to ramp the p-scale by curve view. We're going to keep the p-scale larger than... Actually, no, let's do it. Let's ramp the p-scale by curve view. We're going to say p-scale times ch ramp. So that's generating a ramp. And we're going to call this ramp curve view p-scale curve view. And we're going to drive this ramp with the input of f at curve view. So now we're multiplying this input value by a ramp which is 0 to 1. So you can see it's tiny and getting thicker and thicker and thicker, which is not a bad thing. What I am then going to do is I'm going to say let's fit this to a range, In fact, we can say fit 01 because the output of the ramp is going to be 0 to 1. And we'll say CHF, we'll call this min P scale, and then we're going to fit that to the max of CHF max P scale. Go to the end, missing a bracket. Okay, so now we don't really need this this P scale one here. We can get rid of that. Hit plus. So again, we've got this P scale thing here. What we can do is we can go and delete all spare parameters. That'll get rid of everything. Hit a plus, and we've just got what we need. So if I said 0.121, everything will get thicker over time, which is not a bad thing. It looks like that gas is expanding outwards. And what we might want to do is we'll also set density. Density will be read onto the into the rasterization, and will multiply down the density of the volume equals ch ramp. We're just going to leap this to 0 to 1, so we don't need to multiply. Density curve view. Cool. Okay, yep, it helps if you actually tell it to use curve view. There we go. Okay, so now we can invert this ramp. So things fade off, and I'll probably do something like this, so it starts to fade off a little bit more aggressively. Okay, now one of the things you might notice is that we're getting this clipping. Now the reason we're getting this clipping is because the bounding box of this volume is not big enough for the radius that we're feeding in on the P scale. This volume will be clamped to exactly to the scale of the points. So wherever the points finish, that is where the volume will end. But we can use this bounds node. So this creates a bounding box around input geometry. And what I'm going to do is I'm going to copy this max P scale value, and that's what I do. I'm going to paste in that as a relative reference to all of these. So now we know that the padding will cover everything. So there's no clipping now, which is cool. So now we've got this nice volume that grows. It's got some movement. This is not bad. Not bad at all. It looks a bit sparse down the end, but obviously, again, this is a procedural setup. We can go and we can say, give me 100 curves. It'll take everything, it'll cook it through, and there we go. This already is pretty close. Now there's only one thing left that I think we need to do really to complete this effect, and that is to break up this shape and make it look a little bit more natural. So let's do that now. There we go. Cool. Right. So what we'll do is we're going to create a volume VOP. So this volume VOP, I'm going to leave a little bit of space here because I'm going to have a couple of nodes in here in a second, but I want to give you the reason why we're using it first. So volume VOP, we can operate on the volumes. We're going to create an anti-alias noise. Other noises are available, but I like this one. We're not going to set this one to evolving, I don't think. I think there's going to be enough movement elsewhere. But I will keep the vector to vector 4 in, just in case I change my mind later. The reason I like to set it in before is if you promote all your parameters when it's set to vector 3, and then you put this node in, then you've got to recreate all your parameters, which is a pain in the bum. So we're going to do something called volume displacement now. And what that does is it uses a volume sample node to look at its position in space and see what the value of a volume is there. So it's going to be looking up density in a certain location. By moving the position with a noise, instead of saying, look here for what value it is, this position here might look and say, oh, there's some density there, so there's some density here. It's like it's pushing the density around using a noise. So if I create a volume sample, there we go. I'm going to plug in the sample position from here, which is the result of the noise, add the position. I'm going to tell it to look at the first input. It will return a value, and if I plug this in, you should see an immediate change in this volume over here. Cool. So look, that volume has pushed everything around and it looks way nicer. One thing I would say is I might want the amplitude of this noise to be able to grow down the length of the volume. Now we don't have access to the curve view information because this volume only has density, it doesn't have anything else. But what we can do is if we feed in the points as a second input, we can access that point data. We have a position that we're working with. We're going to use the undisplaced position, and I'm going to plug that into a point cloud open. So this is a way of looking at points, multiple points, in a VOP context. In a wrangle context, I tend to use near points. I sometimes use point clouds, but here I'm going to use just the base point clouds because I want to use PC open followed by PC filter. So this takes a number of points based on point position and then returns a averaged result. Basically, it's not exactly an average result. It does take distance into account, but this is a really nice method to work with. So curve U. The reason I do this is because you do have access to near point in a VOP context. However, if the points cross over, you can get errors occurring where it's not sure which point to look at. So if this were doing a figure eight and there was a crossover in the middle, it wouldn't be sure whether to return 0 or 1 at certain points, and it looks weird. So the PC filter just provides us with a slightly cleaner result. So I'm going to plug this into there. I'm going to promote from this. I'm going to promote the radius, and I'm going to promote the max points, and I'm going to plug the file into op input 2. So this is the particle stream, and the output, I've set its curve view, but I need it to be a float channel, and then I can plug that into a multiply just here. So this should eliminate the noise over here. Let's just check I've got everything plugged in right. I think so. Let's just, am I getting a different... There we go, it's set to manual. Let's actually update the scene. So there we go, smooth to rough, and it's saying curve view, and it's looking for op input 2, it's looking for P, and yeah, that should all be working. Cool, let's just make sure that my search radius is big enough. There we go. Let's just set this to 2. Now when you're dealing with these point cloud lookups, there is a relationship of how heavy it is going to be between the number of points and the search radius. So you could set this radius even bigger, and it's not going to slow things down because as soon as it hits this maximum number of points, it stops searching. So if it finds 10 points within 0.01 units of its position, it's not going to keep searching out, it will stop. I tend to set this one quite high, and then I just play with the number of points here. Okay, so that's working, it's smooth there, it's rough there, but you know me, I do like it myself a nice little ramp. So I'm just going to grab this one. and I'm going to stick it. Come on, I should have done this in manual mode. Here we go. Stick that there. We've got the ramp control. So I can go up and I can start playing with this as I like to do. I am going to have a little value at the base because I do want some detail there, but I definitely want it to grow. Let's set them all to B-spline. Let's auto-update that, see what change we get. Lovely. Okay, so I would like this to have a little bit more influence. So I'm going to promote the values on this noise. Again, I'm going to set to manual while I promote. Otherwise, it will recook every time I am changing this setup, which will be really annoying. There we go. Now I can set it to auto update. See there, it updates. Could you imagine if that had been updating for every click? That'd have been annoying. Okay, so the first thing I'm going to do, I'm just going to give it a bit more amplitude, just to see what we get. There. I think that will do. Now, you'll notice that the cut time is quite slow. It's quite chuggy. There is a reason for that, and that is because it is having to cook this attribute VOP over 1 million times. So where it says voxels, that is how many points of data are in this volume. Now, most of these voxels are empty data. We don't need them. But default Houdini volumes, they're what we call non-sparse. So it's just basically this bounding box is full of data. If I were to go to somewhere where it was a slightly more problematic shape, let's have a little look. The voxel size will increase dramatically. So there, this is a much bigger volume, and if we look at the number of voxels we're working with, it's probably around there, 1.7 million. However, we have access in Houdini to VDBs, so we can convert to VDBs. Oops, not a regular convert, we need convert VDB. There we go. Plug that in. Set to manual mode. Just while I change this to VDB, and just have a look at the difference in voxel number. We're at 287,000, so that's way lower, and as a result your calculations here will be way quicker. The only problem is, if we do a visualize tree, this will demonstrate where your voxels are. If you want a rough idea, you can keep it on this leaf nodes and active tiles. This is nice. So these are the active voxels. So before, all of this was filled with data. And it's culled that out now, so there is no data here. But because we're displacing and sampling from positions that are outside of this range of active voxels, we're getting clamped values. But fortunately, we have another node called VDB Activate. And there's a tab on this called Expand. And we can tell it how many voxels do we want it to expand. Let's say 10. So it pushes that outwards. And you can see now we're not going to get that same clipping. We've got a nicer result here now. Cool. Okay, let's just quickly go up here. I'm going to, let's think. I'm going to increase the length of this trail slightly to 36. I'm going to very slightly increase the amplitude of this noise to 9. So it should be spreading out a little bit more. There we go. And I'm going to increase the number of curves that we're working on to 50. So way more points going on now, but that's okay. There we go. That looks cool. Now what I think I might want to do is I might want to break up the to lower the density so it's not as thick throughout the whole length, because obviously more points equals more density when it rasterizes. So on here I'm going to change, let's call this attribute wrangle rasterize atters. Let's go on to mouse up, So I have to cook that because I've changed the name. On mouse up, there we go. I'm going to change this ramp because when you change the ramp on mouse up, it won't change the value, it won't recook until you release that mouse button, and then it will cook, and then it will give you your result at the end. There we go, that's a bit softer. I might just increase this to 0.1, so it does have a little bit of value there instead of just being a 0 density. Let's just remove this point as well. Boink, there we go. And you know what? I said I wasn't going to add evolution, but I am going to add a little bit of evolution to this. So one of the cool things, just quickly, about this volume VOP here is you could have one, let's say I've got one which is quite a low frequency noise, and what I want to do is have a second one which adds high frequency noise. I can just copy this node, paste it in. Let's go on to a manual mode, because this does get a little bit heavy to cook now. In fact, is this going to be a crash? No! Whoa, we got away with it. Happy days. Cool, so I'll wire this into the output there. Now what I want to do is I kind of want the inverse here. I want lots of small, low amplitude detail to be added here, and then it to soften out. So what I'm going to do is I'm going to set this to a value of 2. I'm going to set it to an amplitude of 0.5, and I'm going to change this ramp to be very present at the start and then to become not very present. The reason I want this to be a low amplitude one is because I still want to keep things quite tight around here. So if I click update, we should see a reasonable change down here, but not a lot going on up here change wise. Drum roll, please. Cool, there we go, look, we've got some nice breakup there. It gets nice and soft there. I like this, I think this is good. Cool, okay, the final thing I'm going to do is I'm going to throw down a VDB activate again, because I had to expand out the number of voxels I was looking at up here, but there was probably still some dead voxels, so if I put it into there and say deactivate, it will deactivate 0 value voxels. So we've gone from 1.4 megavoxels to 0.8 megavoxels. So we've got a nice clean setup. And I'm going to say create a null, and I'll call this out. Right, I'm going to look through the camera. I'm going to do a little flipbook of this. A general tip I always have is to save before you do a flipbook, because I've had a lot of instances of flipbook causing my scene to crash, which is never fun. Okay, so I'll see you when this is finished flipbooking. Okay, so here we go. That sequence is fully cooked out. You can see the results here are pretty nice. The smoke definitely looks like it's expanding and spreading out as it goes. There's some nice motion you can see going on internally. Looks like there's currents of airs and eddies going around. I would entirely buy this as an effect in a show. And remember, this is fully procedural. You can go in and change anything in this at any time. If you wanted to think, oh, maybe this is a little bit too dense, it's very, very simple to go in and multiply down the density value here by, say, let's say 0.25. Let's see what results we get from that. You know, it's very quick to iterate and to stack up these changes to get something that becomes very, very different. And it's really quick to iterate, so any changes that you need to make, you can make very easily. I hope you found this useful. There's some techniques in here that you can use directly recreating this setup or transporting into other setups. There's definitely things here that I use in multiple different ways, and hopefully we'll see you again for another video, and good night.